Hey everyone, it's Mr. Ray with our next lesson in grade 11 University Math. We are working in the trigonometry unit, and we're going to finish off the unit by talking about a new topic called trigonometric identities. I know it sounds complex, but basically we'll talk what it is in a second. This is something that you'll be continuing on into grade 12, and believe me, it gets much more difficult in grade 12. So you may think that the concept is difficult, but I think if you practice these, you'll see that they're actually pretty straightforward on how to do these. Okay, so what is an identity? An identity looks like an equation, but you're not going to try to solve it. What you're trying to do every time is prove that for every variable, this equation will always be true. The left side will always equal the right side. So in other words, you could plug in any value for the variable possible and the equation will be true. Okay, so you'll see what I mean by that when we start the examples, but it's really different than solving equations. In fact, it's almost completely opposite. So here's another way of putting it, which I've kind of talked about. Trig identity is a relation among trigonometric ratios. So there'll be lots of references to sine, cos, tan, the reciprocal identities, the reciprocal ratios. And it looks pretty complicated when you first look at it, but it's just a matter of converting it so that you can show that both sides are actually the same, and therefore any value you plug in for the variable will be true for that equation. Now, what do we use to prove this? Well, we start with these basic identities. So these things are confirmed to be true, and we can use them anytime we want. So these are the Pythagorean identity, quotient identity, and reciprocal. So you've seen the last two here. This Pythagorean identity, this comes from when we were working with the angles and the ratios with different angles a couple of lessons ago. And remember we had the formula x squared plus y squared equals r squared. Okay, and that was because, you know, with these trig ratios, they work from the right triangle, where we have x, y as our two sides along with the hypotenuse, which is really the radius. Okay, now for the unit circle, r is equal to 1. So this actually converts into this identity here. So this is the official Pythagorean identity. So where did these sine squared and cos squared come from? Well, remember x is equal to cos. Well, x is equal to cos x, y is equal to sine x, because y and x, we learned this unit that we can refer to them on the unit circle. The x coordinate is the cos of the angle, and the y coordinate is the sine of the angle. So we basically change this formula into cos x squared plus sine x squared equals 1. Okay, now we don't, in math, we don't write cos x squared as in this form. The main reason is if you wrote cos x squared without the brackets, it looks like you're taking the cosine of the angle that's x squared. So that leads to problems. So officially, you can say that cos x, if you square it, that you can write that as cos squared x. And same thing for sine x. If you square that, you get sine squared x. I know that looks a little different, but that's just the way we write it. Okay, so I can now change this to cos squared x plus sine squared x equals 1, and this is the same version of that equation with the sine and the cos reversed. So this is probably your most important identity, primary identity that you'll be using to prove other identities. Now this can be actually rearranged, and you'll see this quite a bit in this lesson. For example, if I subtracted sine squared theta from both sides, I get cos squared theta equals 1 minus sine squared theta. Or if I subtracted cos squared theta from both sides, I'd get sine squared theta equals 1 minus cos squared theta. So you get really used to seeing these and knowing what you can do with them. Okay, so for example, if you saw something that said 1 minus sine squared theta, you could immediately change that to cos squared theta. That's okay. That's an official identity. These other ones you've already seen. You know that sine theta is equal to y, and cos theta is equal to x, and tan theta is also equal to y over x. So this is a very basic identity, that tan theta is sine theta divided by cos theta. So that will come up quite a bit. And also these reciprocal identities, these are just a definition of the reciprocal ratios. Now, these two last ones, part of the strategy of solving trig identities is to try to convert everything into sine and cos. For example, these secondary reciprocal ratios, we can easily convert them into sine, cos, and tan. We can actually, this one here, I'd like you to rewrite this one, because this is a headache, because then you've got to convert tan afterwards. So cotan theta is really, so tan theta was sine theta over cos theta, and cotan is the reciprocal, so it's really cos theta over sine theta. So that's the version I'd like you to use, rather than do the two conversions, first from cotan to tan, and then from tan to sine over cos. So this is a lot quicker and more efficient. So these two identities here, what you're going to be using those for is what I was talking about, the strategy that you want to change any non-sine and cos ratios into those ratios. So instead of working with 6 potential ratios, you're only working with 2. Okay, and then the Pythagorean identity usually comes in later on when you're doing some work on each side. You might come up with something where you can use one of these versions of the Pythagorean identity. You'll see those. So the whole strategy, like I talked about, we're going to be starting with these proven identities, use them to prove other more complex identities. Okay. All right, so we'll forget about that one for now. So here's the way you start with identities. So when you see that, it always says prove that. So you're proving that this is going to be always true. So one thing you can't do is just find a value of x that seems to work. Okay, that's not proving it works for every value. So that strategy would be totally false, because you can't possibly test every value. So what you want to do is, I'm going to take the left side of this equation and write it as ls, and write whatever on the left side, cos x tan x over sine x. And then way over here, totally separate from that, I'm going to write right side equals, in this case it's just 1. So the whole idea here, and the best way to explain it is you have to act like there's a brick wall between these two sides. You can't do things like you did with solving equations, like multiplying both sides by something or adding a number to both sides. You can't do that. The only thing you can do is independently work with each side and try to convert it so that it looks like the other side. So where do we start? So the next key strategy is to pick the side that's most complicated looking, and that could be the most number of ratios, or the more terms, or just something that looks harder to work with. So in this case, this is really a no-brainer. I mean, there's not a whole lot I can do with 1, but there's a lot of simplifying and changing around I can do with the left side. So we're going to start with the left side and hopefully turn this in through our legal identities that we've talked about up here. We want to turn this expression into 1. And when you first start these, you really don't have a clue how like the whole strategy. Very few people do that, and I'm going to get 1. You kind of take it step by step, see what you've got, work with that next step, okay? And sometimes you'll do everything legal and not get anywhere, and you realize, okay, I have to try a different strategy, so you go back. So it can be frustrating because sometimes you'll do everything right and you still have to try a different strategy. So let's just dive into this. So we're definitely starting with the left side. So remember the strategy I talked about earlier is to change any non-cos or sine ratios into cos and sine. So we know that tan x is equal to, well, it'll be sine x over cos x. So that's the first thing we're going to do. So we've got cos x, and then I'm going to put right here, I'm going to put times sine x over cos x all over sine x. So I know that looks like it's getting messier than it did before, but now we can be working with just sines and coses in terms of what we've got here. So on the top here, this is actually good news because cos x, I could write that as cos x over 1 times sine x over cos x. So I've actually got a cos x on the top and bottom of the numerator here. So maybe just to make it a little bit more clear, I'll write it as cos x over 1. So now you know why I'm doing it, because I'm working with basically 2 rational expressions here. So I've got cos x. I can cancel those out because I'm multiplying. Okay, and what am I left with here? Well, all of a sudden everything's looking like roses, because on the top now I just have sine x left over, and I'm dividing that by sine x, which take something and divide it by itself, you always get 1. Okay, so we've basically proven that this is actually always going to be equal to 1. So our proof is complete. The bottom line on each of these has to have the same value. Okay, it can't be something different here compared to something different here. Otherwise, your proof is not complete. Maybe you didn't see that, so let's try that again. So I changed the cos x to cos x over 1, tan x to sine x over cos x, and the cos x canceled out, left with sine x on the top, sine x on the bottom. That's equal to 1, and you can see we have the same answer for left side and right side in terms of what we've converted. So that means our proof is complete. So the next part that you always have to have is an official thing saying therefore left side equals right side. The way I've broken these into 2 separate sides, left side equals, work with that, right side equals, work with that. I didn't really do anything with this. And then once you get them the same expression for left side and right side, you can now state that, and your proof is now complete. Okay, you cannot treat this like just an equation and just work with both sides with an equal sign in between. You will lose major marks because you're not solving any equation, you're proving an identity, which is different. Okay, so don't lose marks because you're not setting up the form correctly. Okay, so here's our next one. So again, I'm going to set this up like an identity. So the left side in this case is cos x. Over here on the other side of the brick wall, right side equals 1 over cos x minus sine x tan x. So that's multiplying. Okay, so really no question which side is more complex in this case. It's definitely the right side. So we're going to work with this, and hopefully eventually it changes into cos x. So you can see we've got a tan x over here. So that's the first thing I'm going to change, is change the tan x into sin x over cos x. So I got 1 over cos x minus, and I'll write the sin x again as sin x over 1, just so you can really see that it, you know, what it looks like as a fraction. And then I've got the tan x as sin x over cos x. Okay, so all I've done in this second line here is change the tan x to sin x over cos x, and just make this sin x look like a fraction, because I'm going to multiply these two fractions in this step. So I've got 1 over cos x, that hasn't changed at all, minus, now on the top I've got excuse me, I've got sin x times sin x. So remember, that's like sin x squared, but we don't write it like that. We write it as sin squared x, which is basically sin x squared. Okay, and on the bottom, 1 times cos x is cos x. Now, the good news here, I've got the same denominator with these rational expressions, cos x on the bottom, so I don't really have to manipulate anything. I can combine these into one rational expression. So on the top, I've got, well, let's do the bottom. The bottom is cos x. And on the top, I've got 1 minus sin squared x. Okay, and you may think, oh, I have no clue what to do now, but remember our basic trig identities, the different Pythagorean identities. So you can see here, 1 minus sin squared x. Well, the actual variable doesn't matter. 1 minus sin squared x would be equal to cos squared x. So I can use that identity and convert the numerator to just cos squared x over cos x. Okay, now cos squared x, remember that's like cos x times cos x. So I can basically cancel one of the cos x's with the bottom, and lo and behold, what are we left with? Cos x. And that's what we were trying to do. So we basically prove that the left side equals the right side. So we have to state that. That will conclude our proof that this is always true. The original statement, cos x equals 1 over cos x minus sin x tan x, that's always going to be true, regardless of whatever angle I put in there. Okay, now one other strategy I might just mention. We didn't really have to do it this time, but sometimes you'll do a couple things and you feel like you're making it look worse and you're a little frustrated. So sometimes it's worth taking a second, just peek over and remind yourself, what am I trying to get this to look like, right? And sometimes that helps you out, because maybe you're very close and you don't realize it, and you think, well, maybe I just got to change part of this so that it becomes something else, and then I'll be done. So I wouldn't do this work blindly. I would start it off fairly blindly, but once you get going, take a peek over there and remind yourself, what am I trying to get? And sometimes that helps you with your strategy. Okay, we haven't really had to do that yet, but you'll see questions where you do. Example 3. So this identity, again, is looking a little more complex. We have to prove that sin squared x over 1 minus cos x is equal to 1 plus cos x. So this is definitely the hardest one so far. So again, set it up the same way. You've got your left side over here, sin squared x, 1 minus cos x. And the right side over here is 1 plus cos x. Now this one's not quite as obvious as to which one's the more complex statement. This one has two terms, but this one's a rational expression. But I think the thing that makes it really more complex is what you have in the denominator, 1 minus cos x. That might be kind of hard to get rid of. So we're gonna start with this. Sometimes you can get to a point and you can stop and maybe work from this. I don't think any of these examples we need to do that, but in grade 12 that's often a strategy, is to work with both sides and come up with a common last statement or expressions that are the same. Okay, so where do we go from here? Everything's sine or cos, so we don't do the changes. So it seems like there's not much we can do. I could change this to 1 minus cos squared x, and that might be that. I think that would actually work if you did some factoring, but I won't talk about that. I'm going to just try this strategy that always seems to work, and that's, I want to basically try to simplify the denominator so that I have one term. So the strategy here is always, if you have like 1 plus or minus cos x or sine x or cos x plus or minus 1, if you have something that looks like that, two terms, what we're going to do is actually trying to, it's not really rationalizing the denominator, but what we're going to do is multiply both sides by what we call the conjugate. So let's just put our first expression here. I'm going to put the bottom in brackets because we're going to multiply. So what we're going to do is multiply by the conjugate of this. Now the conjugate sounds complicated, but it's not. It's just a binomial where the conjugate has a different sign in between the two terms. So it's the same two terms, 1 and cos x, but it's 1 plus cos x. And we do the same thing on the top because we have to keep it the same. So it definitely looks like we're making this worse, but you'll see the strategy really cleans up nicely. So when we multiply that out, let's see, I could distribute this, but you'll see why I don't in a second. So I'm going to leave it just the way it is on the top, where I don't really distribute across the brackets. Now down at the bottom here, if you think of these as factors, these are like difference of squares factors, and they are, because if I actually do my FOIL here and multiply it out, you can see the two middle terms are plus cos x and minus cos x. So they actually cancel out, and the only thing that's left over is this term squared minus this term squared. So you always end up with something like this. Now you could do the long version of multiplying across, but if you realize this is just a difference of squares, so it turns into that. Now here's where we can go back to our original identities that we can use. This should seem familiar. 1 minus cos squared x is going to be equal to sine squared x. So I can immediately change. The top will keep the same, but the bottom changes to sine squared x. And look what we see here. We've got sine squared x on the top and on the bottom, and they're both multiplying. Well, at least the top one is. So you can cancel these two sine squared x, and what are you left with? 1 plus cos x. And that is exactly what the right side is. So mission accomplished. We have left side equal right side, and we're done. Okay, now you may think that when I'm doing this that, I see every step ahead, but the reality is most people don't. They just try to work what they've got, and after a while you get used to a couple strategies like this multiplication by the conjugate, and as soon as you see something else that's like that, you'll say, oh, I know what I got to do, because you've done something like it before. So familiarity with previous questions is a real advantage. So if you see a strategy that works, chances are you're going to be using it again sometime soon. Okay, so that's our third example. Let's do a couple more. Okay, so this one, probably the most complicated of them all. So write them out in the correct form. So I've got 1 over 1 minus sine x minus 1 over 1 plus sine x. And then the right side is equal to 2 tan x over cos x. Okay, now we do have a tan x here in a single expression. So that's a little bit complicated, but not really compared to this. Here we've got two different terms. It's always easier to change two terms into one term than it is to go the other way around. So right away, the fact that this is two terms and I've got this strange binomial denominators that aren't the same, that's really what I should do. So we're going to start with this one. If need be, we could do a little bit of work with this and change it into something simpler that hopefully equals this. But there's a pretty good chance I can actually do all the work on this side. So the first thing I see, I want to combine these into one term. So this is like fractions with different denominators. We want to combine them, so we have to have a common denominator. So that common denominator will be basically both of these factors multiplying. So I'll do that. So once I combine these, the bottom will look like this. So 1 minus sine x, 1 plus sine x. So in order to get the first term to have that denominator, I have to multiply it by 1 plus sine x. So since it's only 1, multiplying by 1, I'll just put basically 1 times that here. And then I'm subtracting, and here I need the 1 minus sine x to complete the denominator, common denominator. So this will be minus 1 minus sine x. So hopefully you can see that, how that works. If it takes a couple extra steps, that's fine. But this is what it boils down to. Now we can definitely simplify across the top, just combining everything. So we're going to do that. So if I read across here, I got 1 plus sine x minus 1. So that means the 1's just canceled out. And then I've got minus negative sine x, so that's like a plus sine x. So what do I have at the end here? I have 2 times sine x. Okay, now that's, if you take a peek across here, that's, that's promising. I've got a 2 on the top here, but I don't have a tan, I've got a sine. So we'll see how we can work with that. Now on the bottom here, remember when we multiply this, just like the last question, this is like difference of squares factors. So if I multiply these together, I end up with a 1 minus sine squared x. Okay, and I won't turn back to it this time, but 1 minus sine squared x is equal to cos squared x. So I have 2 sine x over cos squared x. Okay, so now when I peek back over, okay, well, look, I've got a cos x here and a cos squared x here. So I kind of have an extra cos x on the bottom. But instead of a sine, I have a tan. So I'm just going to continue on up here. So what I'm going to do, I can kind of see where that tan's coming from because tan is sine over cos. So I'm just going to write this so it's a little bit more obvious. So on the top, I've got my 2 sine x. On the bottom, instead of writing cos squared x, I'm going to write cos x times cos x. You don't have to do this step. It just, to me, you can see where this is coming from. So at this point now, here's my sine x over cos x. If I circle that, I know I can convert that into a tan x on the top. So this is equal to 2 tan x over cos x. And again, I've got this to be exactly the same as the right side. So left side equals right side. Proof is finished. And we know that this identity is true. Okay. Now, we always, when we're doing trig identities, we're always proving that they are an identity. And you have to use this method to do that. If you ever want to disprove an identity, it's a lot easier. Well, in some ways it is. To prove something's not true, you only have to come up with one example where it's not true. So if I could ever do that, if somebody asked me to prove this is wrong, I just need to come up with one value that it doesn't work for, and it's no longer true as an identity. So that's just to keep it in mind. So if you're trying to prove an identity is true, you have to basically go through these series of steps to prove that it's always true. It doesn't depend on the value of the variable. Okay, last question here, and this is kind of a physics equation here. It's two different formulas for height. We don't really have to understand where they came from, but this is equal to height in one formula, and this is also equal to height in another formula, and we want to prove that this is always going to be true. So basically prove that this is an identity. So we're going to do it the same way we did with the other ones, even though we've got these kind of strange looking, I think it's velocity, initial velocity values, and this G here. So don't really have to understand what they're there for. We could just work with the mathematics part of it. So the left side here, we've got this equation, VO squared sine squared x over 2G. And over on the right side, we've got VO squared cos squared x tan squared x over 2G. So when I first look at this, obviously this one's more complicated, so we will work with it. But I see a lot of good news here. I see that both of them have that VO squared on the top. I see both of them have the 2G on the bottom. So really it kind of boils down to, I need to prove that sine squared x equals this. Okay, so I will be working with this side, and this is not nearly as intimidating as it looks. So the first thing we're going to do is change the tan squared x into its identity. I'm also going to change, like I did previously, put the 2G here, I'm going to change cos squared x into cos squared x over 1. You don't have to again, but it makes some of the fraction work a little bit more obvious. Now the tan squared x, you know that tan x is sine x over cos x. So if I squared tan x, I would get sine squared x over cos squared x. Okay, so that's the only thing I've really changed other than write cos squared x as a fraction. Now you can see right away what we're going to do here. We've got cos squared x on the top and on the bottom of this multiplication, so they can definitely cancel out. And what do we have left? We have VO squared sine squared x over 2G, and that's exactly what we have on the left side. So therefore left side equals right side. Okay, so you've seen a few examples of how to do identities, trig identities. Hopefully you have enough that you could get started. Definitely practice. You can't just look at somebody else doing these and be able to do one of these on a test. It requires basically practicing all the questions you can. Okay, and treat these identities sort of like a puzzle. Okay, they could be frustrating if you let them, but treat it like a challenge that you're going to try to show that these two things are the same with the tools that you can use to do that. So the strategies I've talked about are very sound. There's probably a couple other strategies, that we can talk about in the class, but for grade 11 trig identities, this is about how tough it can get. Grade 12 gets a lot more difficult. Okay, so that'll be it for this lesson. Hopefully you get an understanding of what trig identities are and some of the strategies we use to show them. Also, extremely critical that you prove identities in the right form, that you break the left side and right side into two separate parts, only work with one at a time, not with each other, and end up showing that that each side does come to the same expression. So therefore they are the same. Therefore the initial equation is an identity. Okay, so that's it for today. Have a great day, and we'll see you next class.